And let's go through a couple of examples of weight and also acceleration due to gravity. Okay. So we see here that weight is the name given to the attractive force of an object due to gravity. Okay, and weighed a few things around the room and came up with this table. Here's the mass of the object and the weight of the object. In fact, we think of mass and weight as almost interchangeable, but to the physicists, they're different items. Mass, of course, is how much stuff is there. Weight is the pull on it toward the center of the Earth or to another object. And as we expect, an object that's more massive also has more weight. Let's take a look at that weight versus mass ratio. In this case, we have 1.5 newtons divided by 0.15 kilograms. Okay, for the numeric part, we see 1.5 divided by 0.15. We know that's 10. But how about these units? The newton divided by a kilogram. And just a reminder that a newton is the force required to accelerate 1 kilogram at a rate of 1 meter per second squared. So we can see if we have a newton per kilogram, the kilograms will cancel. So this is really meters per second squared. We could also call it the newton per kilogram. Both are correct. When we're dealing with weight, sometimes this ends up actually being a good unit. So I'll put both up here, either the newton per kilogram or the meter per second squared. Let's go down the rest of these. 3.5 divided by 0.35, you can see that that is also 10 newtons per kilogram or meters per second squared. Let me finish out the rest of that. 5.5 divided by 5, again, guess what? It's 10. 7.5 newtons and 0.75, again we have 10 newtons per kilogram. We're probably starting to see a pattern here. And this last one, something that has a mass of 1 kilogram will have a weight of about 10 newtons. Of course, we take that some other place in the universe, on the moon, and the force of gravity is not as strong. Now this may be just a result of the accuracy of our scale. Those who are a bit pickier about this will know that that value, if we're very careful about measuring, it is 9.8 meters per second squared. Let's go ahead here. So the weight in newtons is equal to, right now I'll just call it 10 newtons per kilogram times the mass of something in kilograms. We can see with that our weight would be, we'd cancel both those kilograms, and we'd have weight in newtons. Now recall that the force of gravity is the thing that gives objects weight, but it's also the thing that makes things fall if we don't hold on to them tightly enough. And so in this case, we made some measurements for a book that happened to be 2 kilograms. It was dropped, and we had some precision instruments that measured its position every 0.05 seconds. And the position was recorded here. By now, you're pretty, good at calculating velocity in meters per second. We've done it at many of our labs. And just kind of show you this. Okay, so how far did we go? From 0 to 0.05 seconds. Our distance in this case was 0.013 meters. And our time that elapsed was 0.05 seconds. We can see that we get 0.26 meters per second. And I think you could pretty well do the rest of those calculations. What we want to look at is acceleration. Remember, acceleration is our change in velocity divided by a change in time. So let's go ahead and note this. Our velocity changed from 0.26 to 0.76, so our velocity changed 0.5. Our units are described here in meters per second. Again, from 0.76 to 1.26, 0.5 meters per second. And then 1.26 to 1.76, 0.5 meters per second. Now to figure out the acceleration, we'll take our change in velocity and we're going to divide it by our change in time. Let me just kind of work over to the side here. We know our change of velocity is 0.5 meters per second. My change in time from one unit or from one incident to the next is 0.05 seconds. Take a look at this. 0.05 divided by 0.5 divided by 0.05, guess what? 10 meters per second squared. I would make sure that I put the units here because they're not listed up here. Or maybe to save time, I could put them up here now that I know what they are. Okay, so let's talk about what we just ended up seeing. On that last one, we saw that acceleration we know is equal to the net force divided by mass, or we could rearrange that the net force is equal to mass times acceleration. We've seen this in a few of our labs so far. And when the acceleration is due to gravity, we have a special symbol just for the acceleration due to gravity, and that's the letter G. We can replace our net force, if it's only gravitational force, F sub G, which we also call weight. So the weight of something is equal to the mass times the acceleration due to gravity. Normally that'll be the gravity due to the acceleration on the Earth. If we go to other places, it'll be the acceleration due to gravity on that local planet. Okay, so in this equation we know that F sub G is the force due to gravity. We can also call that weight. M is mass measured in kilograms, and G is the acceleration due to gravity. We've been using the values either 9.8 meters per second squared or 10 meters per second squared. Okay, so we know as intuitively, as mass goes up, so does the force due to gravity. Okay, so there's a direct relationship. As mass increases, gravity increases. Okay, and as both the force goes up and the mass goes up, the acceleration then actually remains the same for all objects. So all objects fall at the same rate. Okay, so far we've been looking at the force due to gravity, but something that might be important is, hey, can I predict how far something will fall? Okay. And we know that the position or the change of position is the average velocity times the time that something is falling. Okay, and the idea of average velocity comes in very handy if our velocity is changing. We see that when there is acceleration. Okay. So acceleration is our known rate of increase in velocity. So that should be able to give us some idea about how far something has fallen. Okay, and so this next section is going to involve a little bit of mathematics. If you just want to pay attention to the final formulas, that's fine. If you want to see how this works, it might be helpful. Okay, so we're defining a few things. X is our position. We have an average velocity. Our velocity at some particular time, either our initial or starting velocity here, or our final velocity, the time something has been falling, and then the acceleration. Will be handy now is that our acceleration will be due to gravity. Okay. So we see that the position that something has attained, or how far it's moved, is the average velocity times the time. Hey, but if something is varying, an easy way to take a look at its the average velocity is to take the ending velocity plus the beginning velocity and divide by 2. That assumes that it's changing velocity uniformly, or that acceleration is constant, okay, which would be the case if something was falling. Let's just take a look at that. So we know that our final velocity is really our acceleration times our time. That's assuming that we're starting at a velocity of 0. Yep, and we've got that listed here. So if I want to go through and do a little substitution, I know my average velocity is my final velocity divided by 2, assuming that I started at 0 velocity. So I can see it's acceleration times time. That's our final velocity divided by 2. Remember that the distance that we've traveled is our average velocity times time. Now this has become our average velocity, 1/2 times the acceleration times t. We can combine these t's to get t squared. So now our position equals, for accelerated motion starting from rest, 1/2 acceleration times t squared. Now remember, for objects that are falling, we use that special symbol to replace the generic acceleration with g for the acceleration due to gravity. Okay. So for those who didn't want to follow those steps, this will be kind of the important formula that you want to see, is that the distance something falls is equal to 1/2 times the acceleration due to gravity times time squared. Let's take a look at a couple of example problems that reinforce what we've just seen. Okay, so we have Mr. Carey hangs a 1 kilogram frog, so we know what its mass is, from a spring scale with a string, and the frog is at rest. Okay, so let's draw a force diagram for the situation. Looks a lot like what we did in class a couple days ago. So we have our frog at rest, hanging from a spring scale. We see we have the tension force upward, the gravitational force downward on the frog. These two items are balanced. How do we know it's balanced? Because the frog is at rest. So he's at constant velocity, or in this case, the special case that his velocity is 0. Okay. So what does the spring scale read? Okay. We know that weight is proportional to mass, okay, and that the force of gravity is also going to be equal to the tension force up because it's at rest. And so we know that mass times gravity is going to be the weight of our frog. Okay, he has a mass of 1 kilogram times our gravitational, what's the attraction of 1 Newton for every kilogram. For every kilogram we have, each of those is attracted to the Earth with a force of 9.8 newtons. So our frog here has a weight of 9.8 newtons. And mentioned in class, we can round that to 10 in most cases. Okay, now just like we did in class, although we did it with something other than a frog, okay, Mr. Carey cuts the string and the frog begins to fall. Okay, let's take a look at the force diagram. Okay, so we see that our frog is falling. All that means that we've gotten rid of the tension force. We can see that here we've got rid of tension force. Let me not modify that. Okay, so we only have the force of gravity, the 9.8 newtons. Okay. So here we have a question, 3 seconds after the string is cut, how fast is the frog falling? Okay, we know that anything that's accelerating uniformly, it's just that acceleration times time will give our velocity. We know the acceleration is 9.8 meters per second squared times the 3 seconds. So 29.4 meters per second. For those who like to use 10, this would be about 30 meters per second. Now comes the slightly more complicated problem. Okay, how far has the frog fallen during those 3 seconds? Okay. We could approach this one of 2 ways. One is our newly found formula. 1/2 gt squared is equal to the distance it falls, or it fell. We know gravity, that's 9.8 meters per second squared, and the time is 3 seconds. We don't need to know a final velocity for this, but we can just put in our numbers. 3 squared, okay, it's going to be 9 seconds squared times our 9.8 meters per second squared times 1/2. We get 44.1 meters. Or we could look at it in terms of average velocity times the time. Our average velocity is going to be our starting velocity, 0, when you cut the string, to our final velocity, 29.4 meters per second, found here, and divide that by 2, times the amount of time that has been traveling, 3 meters, let's see, oh, this should only be 3 seconds. Boy, error there. So times 3 seconds, sorry about that. Kind of shows the importance of using units. So our 29.4 meters per second times our 3 seconds, we end up getting that same value, 44.1 meters. Okay, so now it's your turn. Go to the Schoology quiz, the T2 Schoology quiz, and these 3 questions will be found there. Go ahead and answer those. You can use your notes if you'd like.